this problem reads, calculate the displacement and velocity at times of a half a second, 1 second, 1.5 seconds, 2 seconds, and 2.5 seconds for a rock thrown straight down with an initial velocity of magnitude 14 meters per second from the Verranzo Narrows Bridge in New York City. The roadway of this bridge is 70 meters above the water, so you're throwing it down 70 meters above the water. Okay, we're not going to do all 5 parts, but I will do part A and D, so at half a second and at 2 seconds. Let's just see how that problem is impacted with the different times. Okay, so first we want to identify what is our object. We're interested in motion. We want to know the displacement in a player of motion and the speed, or velocity, in a player of motion. And we're interested in that motion of a rock. So what is our initial condition? And what is our final condition? When do we start carrying and when do we stop carrying? Well, we start carrying when the rock leaves our hand. We throw it down, and that's when we start carrying. We stop when it hits that time. And in the first example, that time is a half a second. All right, so here's our rock. It's above the water. And we're going to call this position equal to 0. So we have initial, final position, initial velocity, final velocity, acceleration, and time. So my initial position, well, the rock starts at 0. That's where I've set the origin. I don't know where it ends up a half a second later, so I don't know my final position. My initial velocity, well, I'm told it's at a rate of 14 meters per second. But it's moving down, so I like to use convention. So I'm going to put that as a minus 15 meters per second. I don't know how fast it's going after the half a second, but I do know the acceleration. We're in a free fall situation. It's once it leaves my hand, only gravity's acting. So we know that acceleration is negative 9.8 meters per second. And of course, the time in this example is a half a second. So the problem asks for the displacement and the velocity after a half a second. Well, we want to remember that the displacement is x final minus x initial. So if I need the displacement, I need to know x final. So we'll start with that one. X final, remember, is x initial plus v initial t plus 1/2 our acceleration times our time squared for an accelerating object. Well, we can use this equation. X final, I don't know. We'll leave it at its variable. X initial, well, that's 0. My initial velocity is negative 14.0 times my time of a half a second plus 1/2 negative 9.8 times 0.5 squared. All right, so I end up with x final is equal to, well, negative 14 times a half a second is negative 7.0 plus 0.5 times 9.8 times 0.5 times 0.5, we get 1 plus a negative 1.225 seconds, meters. And so x final is equal to negative 8.22 meters. Now that half, well, I want to use 3 significant figures in my problem, and that half, since that's an even number, stays the even, is rounded to an even, that 5. So we end up with x final is equal to negative 8.22 meters. Now we're also interested in knowing how fast it's going. So we can use our relationship for v final, which tells us that v final is equal to the acceleration times v initial plus the acceleration times time. My final velocity, well, that's minus 14.0 plus a negative 9.8 times 0.5. So negative 14 minus 4.9, and we get negative 18.9 meters per second for our final velocity. All right, so our displacement, which was x final minus x initial is equal to 0. So our displacement is simply x final, negative 8.22 meters, and v final at a negative 18.9 meters per second. Okay, well, how does the problem change if the rock travels for any of those other times? We'll do 2 seconds. Well, we're still interested for when the rock leaves its hand to when it hits that time, but that time now is 2 seconds. So I still start at 0. We still don't know where we end. We still started at negative 14 meters per second. We still don't know how fast it is after 2 seconds. Still in free fall because it left my hand, and now our time, instead of being a half a second, is 2.0 seconds. So nothing really about the problem changes except what we can use for time. So instead of a half a second everywhere, I have 2.0 seconds. Instead of a half a second, I have 2.0 seconds. We're still interested in knowing our final position. The table's hitting. We're still interested in knowing our final position because that's going to give us that displacement. So negative 14 times 2, well, that's negative 28, plus a negative 4.9 times 2 squared. So negative 4.9 times 4 gives us a negative 19.6. And so we get a total displacement of negative 47.6 meters. And since our displacement is still starting at 0, our final position gives us our displacement. Similarly, we will change our velocity relationship to reflect now it traveling for 2.0 seconds instead of half a second. And we get negative 14 plus negative 9.8 times 2, negative 33.6 meters per second. So just changing the time in all of our relationships tells us how far the rock travels in a given amount of time. So recognizing key features. Once it leaves its hand, it's in free fall. So that gives us this acceleration. That's not given in the problem, but we're in free fall. So the acceleration is that due to gravity. Similarly, we know it's moving in the downward direction, so we want to make sure that we're recognizing the direction of motion in our velocity if we use conventions, which I tend to do. So our negative 14 meters per second. All right, good job.